Hi everyone, Mary here, and we're going to continue talking about simple machines. This time we're going to start with pulleys. Now, pulleys are basically just like wheels and axles and levers, but they are basically a wheel and axle that is free to rotate. They also add one more kind of cool thing involved here, and that is tension inside of strings. So we're going to talk a little bit about how tension helps make these crazy pulleys work. Sometimes a pulley will help do what a lot of simple machines do, and that is decrease our input force or multiply the amount of force we input. The other thing that a pulley can do is change the direction of a force. This fellow is trying to raise this barrel, and if he was standing on the ground just trying to lift this barrel up, well, it would be really tricky to raise it much further than the length of his arms. But with a pulley, this is a gizmo, a machine, that will allow him to raise it not only more easily, but change the direction of it. So let's talk about the mechanical advantage of pulleys. It's one of the simplest mechanical advantages to figure out because you have to be able to count, and I have faith that you can count. Here's how this works. Let's say this is the pulley system. We're going to look at system A right here, and I want to lift this weight. Well, if I've got this pulley system, what's going on is these ropes all are connected. It's one rope, and if you remember when we discussed tension in the past, the tension is going to be the same at all points within a rope, as long as there's no slack in the rope. So the tension's the same at every one of these points. The other thing to keep in mind is, remember a couple of the analogies I used long ago and far away. If I have all of the weight of an object held by one rope, the tension up is going to equal that weight down. But remember the analogy of the small child sitting on the swing? If the kid weighs, or the child weighs 100 newtons, but her weight is supported by two ropes, one rope is going to support half 50 newtons, and the other rope is going to support half 50 newtons. This idea right here is one of the reasons we use so many ropes in pulley systems. So here's the general rule of thumb. When you're trying to figure out mechanical advantage for pulleys, you basically count the number of ropes. Tension is the same everywhere in the rope, and ropes that go down, ropes that are pulling downward, do not add to the mechanical advantage, but ropes that pull upward do. So this is how this works. I'm going to change color. So for group A, here's what we've got. I've got one up and one down. One up and another up. And this is like the child on the swing. The weight of this object is being shared between two ropes, and because the weight is shared by two ropes, the force or the tension in each one of these ropes is going to be half the weight. These diagrams right to the side are really, really slick. So this rope is a downward pulling rope. The downward pulling rope does not contribute to mechanical advantage. So what's the mechanical advantage of this system? 1, 2, that one doesn't count. Mechanical advantage is 2. Let's take a look at system B. We've got 1, 2, 3 up ropes and 1 down rope. Down ropes do not contribute to mechanical advantage. So what that means is the weight divided by 3 is going to be the tension in each one of those ropes. Let's look at system C. Now the weight here, we've got 1, 2, 3, and look, the last rope is an up rope, not a down rope, so it does contribute to mechanical advantage. So the weight divided by 4 is going to be the tension in those 4 ropes, and my mechanical advantage of this system is going to be 4. Okay, what I'm going to ask you to do is hit pause. See if you can just figure out the mechanical advantage of each one of these systems, and then we're going to come back and do it together. All right, what's the mechanical advantage in this system? 1. This is a down rope, and down ropes don't add to mechanical advantage. What's the mechanical advantage here? I've got 1, 2 ropes, and up rope does count, so mechanical advantage of 2. System C, 1 rope, 2 ropes, down ropes don't count, mechanical advantage of 2. So why in the world would somebody have setup C versus setup B? Well, depending upon how you're lifting something, having a rope that you pull downward as opposed to pull upward might just be more convenient. What about system D? What's the mechanical advantage? 1, 2, 3 up ropes, and so mechanical advantage of 3. This one, 1, 2, 3. Down rope, does the down rope contribute? It does not. Mechanical advantage of that system is 3. One of the questions you might get asked is something like this. If I have a weight hanging from a pulley system that weighs 100 newtons, what's going to be the force that's exerted on the ceiling? Well, the ceiling is going to have to support 2 things. 1, the weight down below, and we are not including the weight of the pulleys themselves, but if we did, we would also include the weight of the pulleys. This problem, they're not there, but in some problems they will be included. And then we have to figure out what is the tension in the ropes. So if this weighs 100 newtons, I've got 1 up rope, 1 up rope, this is a down rope. My mechanical advantage is 2. So the tension in each rope is going to be 100 newtons divided by 2. And the ceiling is going to have to support not just the weight of the box, and the weight of the pulleys, if that was given. It's also going to have to support the tension caused by the ropes. So if the box was 100 newtons, the tension was 50. What is the force pulling down on the ceiling? 150 newtons. When I was a child, my dad had a repair shop. That was his business. And I remember my father was not a big guy. He was like 170 pounds and 5'7". And I remember him having these great big chain hoists or chain falls up in the ceiling of his shop. And he would hook this up to a huge, massive engine. And my skinny little dad would lift a big engine off the ground using chains. But I remember him standing there and he would pull and pull and pull and pull and pull and pull and pull, because what he gained in mechanical advantage by an outward force of a big force lifted a small distance, he weighed up for with a little force, but he would have to go through yards and yards of chain. I just remember as a kid watching him pull and pull and pull and pull, and the engine just very, very slowly lifted off the ground. Okay, let's talk about inclined planes. Inclined planes, like all simple machines, they allow you to not do the work all at once. So let's say I have a 10 Newton box and I really want to raise it 1 meter off the ground. I could take my 10 meter box and I could go whoop, and I could lift it 1 meter off the ground. I would do 10 Newton meters worth of mechanical work. But let's say I'm feeling kind of wimpy and I don't want to do it that way, so what I could do is use an inclined plane. With an inclined plane, I don't have to put in all of the force all at once. What I can do is maybe apply 1 Newton of force pushing the box, but I have to push it for a lot further displacement, and I will end up with the same output. So if I apply 1 Newton of force for 10 meters, I still do 10 Newton meters of force. These things do not violate any rules of conservation of energy. They just allow you to do a little force for a longer distance to get the same result. Inclined planes, of course, the most common example is a regular old staircase. You don't have to have a staircase in your house. I used to work with a fellow that did not put staircases in his home. He actually had rung over rung hand ladders. Yeah, he was an unusual soul, and that's how he had his family get from one floor to the other floor. I have no clue how they carried laundry baskets up and down those things. But that would be difficult. By having an inclined plane, you get to put in a little bit of force, but you do it over a bigger displacement. Slides are a lot more fun because the force of gravity is distributed over a big displacement, and it's going to hurt a lot less than if a small child would fall that distance. Ouch, we don't want to do that. When you go up on a roller coaster, they can exert a small force over a big displacement as you get to the top of that big hill. Ramps, ladders that are used as an incline, same sort of idea. Now, a screw is an inclined plane that's helically wrapped around an axis. It's nothing but an inclined plane that's been spiraled around some sort of an axis. It's basically a spiral staircase. And that spiral staircase is so nifty because it's nothing but an inclined plane that's just been wrapped. And they're all over the place. When we screw in a light bulb, when we screw the top back on the pickle jar, when you are trying really hard to open a bottle of wine because it's been one of those days, then you use that little cork screw. But it's basically the mechanical advantage of an inclined plane. A wedge is nothing but two inclined planes that are connected back to back. So if I have one inclined plane like this and another inclined plane like that, you now have a wedge. And you might not live in a situation where you cut a lot of wood. That may not be what you do. But if you cut anything from kitchen knives to scissors to chisels, if you're in the medical field, a surgical blade, if you can make this very, 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 very shallow incline, the amount of force that is required will become very, very small if you can make that lever arm big. I've got relatives and things in the medical world, and you want that to be really sharp if it's a surgical blade. You do not want a surgeon having to put in a lot of force. It's a very, very delicate operation. If you look at the business end of a syringe, that's actually on an incline because it's going to have to pierce into skin. If you look at something as simple as a sewing needle that you would put thread in, that is a tiny little wedge at the end of it. So these simple machines are all over your life, and I hope in the future you see more of them. They've been around all the time, but I hope you're just more aware.